Welcome to our deep dive into the fascinating concept of artificial gravity. Today, we're exploring whether it's truly possible to create gravity in space, just like we see in the movies. Artificial gravity has captivated the imagination of scientists and science fiction writers alike for decades. But what exactly is it? And why is it so important for space exploration? Gravity is the force that keeps us grounded here on Earth. It shapes our bodies, affects our health, and influences how we interact with our environment. In space, the lack of gravity leads to a host of challenges for astronauts. Microgravity, often referred to as zero gravity, occurs when objects are in free fall, creating an environment where people and objects appear to float. This might seem fun, but it can have serious effects on the human body over time. Long-term exposure to microgravity can lead to muscle atrophy, bone density loss, and other health issues. These problems make it clear that we need a way to simulate gravity if we're going to embark on long-duration space missions. Artificial gravity could be the solution to these challenges. By creating a force that mimics the pull of gravity, we could help astronauts maintain their health and well-being on extended space journeys. One of the most popular methods proposed for creating artificial gravity is through rotation. By spinning a spacecraft or space station, centrifugal force can create a sensation similar to gravity. Another intriguing approach involves using linear acceleration, where continuous thrust generates a gravity-like force. This method, however, comes with its own set of technical and energy challenges. Magnetic fields and tether systems are also being explored as potential ways to create artificial gravity. Each method has its pros and cons, and researchers are actively investigating which might be the most feasible and effective. Throughout this video, we'll delve into these methods, examine the current state of research, and discuss the technological and engineering challenges that need to be overcome. Join us as we explore the exciting possibilities of artificial gravity and its potential to revolutionize space travel. Isaac Newton's law of gravitation is fundamental to understanding gravity. It states that every mass attracts every other mass with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This law can be expressed mathematically as F equals g times the product of the two masses, divided by the square of the distance between them. Here, F represents the gravitational force, g is the gravitational constant, and m1 and m2 are the masses. Newton's insight was revolutionary because it described a universal force. This force acts between all objects with mass, not just those on Earth. In space, Newton's law explains the orbits of planets, moons, and satellites. The same principles apply whether you're looking at a falling apple or the motion of celestial bodies. This law helps us understand why the Earth orbits the Sun and why the Moon orbits the Earth. It's a key part of classical mechanics, influencing everything from tidal movements to the trajectories of spacecraft. When considering artificial gravity, Newton's law provides a basis for understanding how forces might be generated and manipulated. This foundation is crucial for developing methods to simulate gravity in space environments. For instance, the concept of using centrifugal force to create artificial gravity relies on principles derived from Newton's law. By rotating a spacecraft, we can create a force that acts outward, simulating the effect of gravity. Understanding the inverse square law is also important. The force diminishes with the square of the distance, which is why astronauts in space feel weightless despite Earth's gravitational pull. Newton's law also plays a role in calculating the necessary speed for orbital motion. It allows us to determine the velocities needed for satellites and space stations to maintain stable orbits. This understanding is vital for planning space missions and ensuring the safety and efficiency of spacecraft. It underpins much of our current space technology and exploration strategies. The gravitational constant g is a critical factor in these calculations. Its precise value helps us make accurate predictions and develop reliable space systems. Newton's law is not just theoretical, it has practical applications in the engineering and operation of space missions. From launch to landing, these principles guide our efforts to explore beyond Earth. Artificial gravity concepts often use Newton's law as a starting point. By applying these principles, scientists and engineers can design systems that mimic gravitational forces. These designs must account for the mass and distance involved, ensuring that the generated forces are appropriate for human health and mission requirements. The balance between theoretical knowledge and practical application is key. As we delve deeper into the possibilities of artificial gravity, Newton's law of gravitation remains a cornerstone. It provides the fundamental understanding necessary to innovate and explore new frontiers in space travel. Einstein's theory of general relativity revolutionized our understanding of gravity. Unlike Newton's concept of gravity as a force, Einstein described it as a curvature in space-time. According to general relativity, massive objects like planets and stars warp the fabric of space-time. This curvature causes what we perceive as the force of gravity. Einstein's equations show that the presence of mass and energy determines the geometry of space-time. The more massive an object, the more it warps the surrounding space-time. This theory explains the motion of planets and the bending of light around massive objects. It has been confirmed through numerous experiments and observations. One of the most famous confirmations was the observation of light bending during a solar eclipse. This phenomenon, known as gravitational lensing, supports Einstein's predictions. General relativity also accounts for the precise orbits of planets in ways Newton's laws couldn't. For example, it explains the precession of Mercury's orbit around the Sun. Einstein's theory has practical applications in modern technology. GPS systems, for example, must account for relativistic effects to provide accurate positioning. When considering artificial gravity, general relativity provides a deeper understanding of how gravity works. It helps us explore concepts that go beyond simple Newtonian mechanics. Understanding space-time curvature can inform advanced methods of creating artificial gravity. This includes potential future technologies that manipulate space-time itself. Einstein's equations also guide the design of experiments to test artificial gravity concepts. They provide a framework for understanding how different masses and energy distributions affect space-time. Relativity is crucial for high-precision measurements in space missions. It ensures that we can predict and control the behavior of spacecraft with great accuracy. The theory also has implications for the health of astronauts. It helps us understand how prolonged exposure to different gravitational fields might affect the human body. Exploring artificial gravity through the lens of general relativity opens up new possibilities. It challenges us to think beyond traditional approaches and consider innovative solutions. As we push the boundaries of space travel, Einstein's theory of general relativity remains a fundamental guide. It shapes our understanding of the universe and informs the quest to create artificial gravity. This deeper grasp of gravity's nature is essential for developing effective and sustainable space habitats. It's a key piece of the puzzle in our ongoing exploration of the cosmos. Gravitational forces in space operate differently than what we experience on Earth. In the microgravity environment of space, the effects of gravity are vastly diminished. Objects in space still experience gravity, but they are in a continuous state of free fall. This creates the sensation of weightlessness for astronauts aboard spacecraft. Understanding how gravity works in space is crucial for planning long-duration missions. It affects everything from spacecraft trajectories to the health of the crew. The gravitational pull of the Earth still influences objects in low Earth orbit. This is why satellites and the International Space Station maintain their orbits. As we move farther from Earth, the gravitational influence weakens. However, gravity from other celestial bodies, like the Moon and the Sun, becomes more significant. Spacecraft must navigate these varying gravitational forces to reach their destinations. Precise calculations are needed to ensure successful missions. In deep space, the gravitational forces from distant stars and galaxies also play a role. These forces, though weak, can still affect the path of a spacecraft over long distances. The microgravity environment of space presents unique challenges. Fluids behave differently, and objects don't stay put, complicating daily activities and experiments. Astronauts experience muscle atrophy and bone density loss in microgravity. These health issues highlight the need for solutions like artificial gravity on long missions. Understanding gravitational forces is also important for landing on other planets. The gravity on Mars, for instance, is about 1/3 of Earth's, requiring different strategies for descent and surface operations. Gravitational forces also impact the design of space habitats. Structures must be built to withstand varying forces as they travel through different gravitational fields. The study of gravitational forces extends to the behavior of cosmic phenomena. Black holes, neutron stars, and other extreme environments provide insights into the nature of gravity. Artificial gravity systems must take into account these varying forces. Creating a stable and consistent gravitational environment in space is a complex engineering challenge. Gravitational forces influence not just the physical aspects of space travel, but also the psychological well-being of astronauts. Prolonged weightlessness can affect mental health and cognitive function. Understanding and harnessing gravitational forces is key to the future of space exploration. It informs the development of technologies that will enable humans to live and work in space for extended periods. Microgravity and zero gravity are often used interchangeably, but they describe slightly different conditions. Microgravity refers to a state where gravitational forces are extremely weak, but not entirely absent. In microgravity, objects appear to float as if they are weightless. This condition is commonly experienced by astronauts aboard the International Space Station. Zero gravity, or free fall, describes a condition where no gravitational forces are acting on an object. This is a theoretical concept because in practice, some gravity is always present. Microgravity is a result of continuous free fall while orbiting Earth. The spacecraft and its occupants are falling towards Earth, but moving forward fast enough to stay in orbit. Microgravity environments allow scientists to conduct experiments not possible on Earth. These experiments help us understand fundamental physical and biological processes. Living in microgravity poses unique challenges for astronauts. Their muscles and bones weaken without the constant pull of gravity. In contrast, zero gravity would imply a complete absence of gravitational forces. This is nearly impossible to achieve in space due to the omnipresence of gravitational fields from celestial bodies. Spacecraft simulate microgravity conditions to prepare astronauts for the effects of weightlessness. These simulations are crucial for training and mission planning. Understanding the difference between microgravity and zero gravity is important for space missions. It helps engineers design appropriate systems for life support and scientific research. Microgravity affects fluid behavior, causing it to form spherical shapes. This phenomenon is due to the surface tension being the dominant force in the absence of gravity. Microgravity conditions also impact the way plants grow. Studying plant growth in space can provide insights for sustainable food production on long-term missions. The term microgravity highlights the small but present gravitational forces. These forces are much weaker than what we experience on Earth, but still influence motion and behavior. In space, microgravity allows for unique manufacturing processes. Researchers are exploring the production of materials that can only be made in these conditions. Understanding microgravity is crucial for developing artificial gravity solutions. These solutions aim to mitigate the adverse effects of prolonged weightlessness on the human body. By exploring the nuances of microgravity and zero gravity, we gain deeper insights into the challenges of space travel. This knowledge is essential for advancing human exploration beyond our planet. Gravity has a profound impact on the human body, shaping our physiology and health. On Earth, gravity affects everything from our bones to our cardiovascular system. In space, the lack of gravity leads to muscle atrophy. Without the constant pull of gravity, muscles weaken and lose mass. Bone density also decreases in microgravity. Astronauts experience significant bone loss during extended space missions. The cardiovascular system adapts to the absence of gravity. Fluids shift towards the upper body, affecting blood pressure and circulation. The vestibular system, which controls balance, is also impacted. Astronauts often experience disorientation and motion sickness. Gravity influences our sense of proprioception, the awareness of body position. In microgravity, this sense can become confused, leading to coordination challenges. The immune system can be compromised in space. Research indicates that microgravity may weaken the body's immune response. Sleep patterns are often disrupted without the natural cues provided by gravity. Astronauts may have difficulty maintaining regular sleep cycles. The eyes can change shape in microgravity, leading to vision problems. This condition, known as spaceflight-associated neuroocular syndrome, affects many astronauts. Gravity impacts fluid distribution in the body. In space, fluids tend to accumulate in the head, causing facial puffiness and nasal congestion. Exercise becomes crucial in a microgravity environment. Astronauts must engage in regular physical activity to mitigate muscle and bone loss. Nutrition needs are also affected by the absence of gravity. Dietary adjustments are necessary to maintain health and counteract the effects of weightlessness. Psychological health is influenced by the gravitational environment. The isolation and confinement of space travel can lead to stress and mental health challenges. Radiation exposure is another concern in space. Without Earth's protective atmosphere, astronauts face higher levels of cosmic radiation. Understanding the effects of gravity on the human body is essential for long-term space exploration. This knowledge helps develop strategies to protect astronauts and ensure mission success. Long-term space missions present unique challenges that require thorough preparation and innovation. The effects of prolonged microgravity on the human body are a major concern. Maintaining physical health is crucial for astronauts on extended missions. Regular exercise and proper nutrition help counteract muscle atrophy and bone density loss. Psychological well-being is equally important. Isolation, confinement, and distance from Earth can lead to stress and mental health issues. Communication with mission control and loved ones helps mitigate these psychological challenges. Regular contact provides emotional support and a sense of connection. Radiation exposure increases on long-term missions, especially beyond Earth's protective magnetosphere. Shielding and protective measures are essential to reduce this risk. Life support systems must be highly reliable and capable of sustaining a crew for extended periods. This includes air, water, and food supply management. Developing self-sustaining habitats is a goal for long-term missions. Growing food in space and recycling resources are key components. Mission planning must account for the duration of the journey and the time spent at the destination. This involves meticulous scheduling and resource allocation. Crew selection is critical for the success of long-term missions. Astronauts must be physically fit, mentally resilient, and able to work well in a team. Training for long-term missions includes simulations and extended stays in environments that mimic space conditions. These exercises prepare astronauts for the challenges they will face. Scientific research is a primary objective of long-term missions. Experiments conducted in space can lead to breakthroughs in various fields. Long-term missions pave the way for future exploration and colonization of other planets. They help us understand how humans can live and thrive in space. The Mars mission is one of the most anticipated long-term missions. It presents an opportunity to test our ability to sustain life on another planet. Technological advancements are driven by the needs of long-term missions. Innovations in propulsion, habitat construction, and life support systems are essential. Learning from long-term missions helps improve the safety and efficiency of future space exploration. Each mission provides valuable data and insights for the next steps in our journey beyond Earth. Health issues in microgravity are a significant concern for astronauts. Muscle atrophy is one of the most immediate effects, as muscles weaken without the resistance of gravity. Bone density loss is another major issue. Astronauts can lose up to 1% of their bone mass per month while in space. Cardiovascular changes occur as well. The heart can become more spherical, and fluid shifts affect blood pressure and circulation. The immune system can be weakened in microgravity. This makes astronauts more susceptible to infections and illnesses. Vision problems, known as spaceflight-associated neuroocular syndrome, affect many astronauts. Changes in fluid distribution can alter the shape of the eye. Sleep disturbances are common in space. The absence of natural light cycles and the stresses of the environment can disrupt sleep patterns. Psychological health is impacted by the isolation and confinement of space travel. Anxiety, depression, and stress are potential issues. Radiation exposure is a significant health risk. Without Earth's atmosphere for protection, astronauts are exposed to higher levels of cosmic radiation. Nutritional needs change in space. Diets must be carefully planned to ensure adequate intake of vitamins and minerals. Fluid shifts in microgravity cause facial puffiness and nasal congestion. This can affect comfort and breathing. Balance and coordination can be disrupted. The vestibular system, which controls balance, is affected by the lack of gravity. Reproductive health is also a concern. The effects of microgravity on human reproduction are not yet fully understood. Regular exercise is crucial to combat the effects of microgravity. Astronauts spend several hours a day exercising to maintain muscle and bone health. Long-term exposure to microgravity can lead to persistent health issues, even after returning to Earth. Recovery and rehabilitation are essential parts of the return process. Research into these health issues helps develop countermeasures and improve the safety of future space missions. Understanding and mitigating these risks is key to the success of long-term space exploration. Muscle atrophy is a significant issue for astronauts in microgravity. Without the resistance of gravity, muscles weaken and lose mass quickly. The lack of regular weight-bearing activity accelerates muscle degradation. Astronauts experience a noticeable decline in strength and endurance. Bone loss is equally concerning in space. Bones lose minerals, becoming more brittle and susceptible to fractures. Microgravity causes a shift in the body's calcium balance. Bones release calcium into the bloodstream, leading to a decrease in bone density. The hips and spine are particularly affected by bone loss. These areas bear the most weight on Earth and are most impacted by the absence of gravity. Muscle atrophy and bone loss can lead to long-term health issues. Astronauts may suffer from osteoporosis and increased fracture risk even after returning to Earth. Counteracting these effects requires rigorous exercise routines. Astronauts use resistance machines and perform weight-bearing exercises daily. Resistance exercise helps maintain muscle mass. It mimics the effects of gravity by providing necessary resistance for muscle contraction. Bone health is supported through impact loading activities. These exercises stimulate bone growth and help retain bone density. Nutrition plays a crucial role in mitigating muscle and bone loss. Adequate intake of protein, calcium, and vitamin D supports muscle and bone health. Pharmaceutical interventions are being explored. Medications that promote bone growth or reduce bone resorption could benefit astronauts. Research into genetic factors may provide insights. Understanding individual susceptibility can help tailor countermeasures for muscle and bone loss. Rehabilitation is essential for returning astronauts. Physical therapy helps restore muscle strength and bone health after prolonged space missions. Continuous monitoring of muscle and bone health is necessary. Regular scans and assessments ensure early detection and intervention for atrophy and bone loss. Addressing muscle atrophy and bone loss is vital for the success of long-term space missions. Effective countermeasures ensure that astronauts remain healthy and capable during and after their missions. Psychological well-being is a critical aspect of long-term space missions. The isolation and confinement of space travel can significantly impact mental health. Astronauts are separated from their families and familiar environments for extended periods. This isolation can lead to feelings of loneliness and homesickness. The confined space of spacecraft and space stations can also contribute to stress. Limited personal space and constant close quarters with other crew members can be challenging. Maintaining a regular communication schedule with loved ones is essential. Regular contact helps mitigate feelings of isolation and provides emotional support. The monotony of daily routines in space can also affect mental health. Lack of variety and repetitive tasks can lead to boredom and decreased motivation. Astronauts must manage high levels of stress. The demands of space missions, combined with the potential for emergencies, require constant vigilance and resilience. Psychological support is provided through counseling and mental health resources. Regular check-ins with psychologists help monitor and address any emerging issues. Sleep disturbances are common in space and can affect mental health. The absence of natural light cycles and the stresses of space travel can disrupt sleep patterns. Ensuring astronauts get adequate rest is crucial for their well-being. Strategies to improve sleep hygiene and create a conducive sleep environment are important. Team dynamics play a significant role in psychological health. Effective communication and conflict resolution skills are essential for maintaining a harmonious crew environment. Crew members are trained to support each other emotionally. Peer support is a valuable resource for coping with the challenges of space travel. Engaging in recreational activities helps alleviate stress. Exercise, hobbies, and social interactions provide necessary mental breaks from work duties. Preparation and training before missions include psychological resilience training. Astronauts learn techniques to manage stress and maintain mental health. Post-mission support is also vital. Reintegration into normal life can be challenging, and ongoing psychological support helps astronauts adjust. Understanding and prioritizing psychological well-being is essential for the success of space missions. A mentally healthy crew is better equipped to handle the demands of space travel and achieve mission objectives. Space habitat stability is crucial for the safety and well-being of astronauts. The design and construction of these habitats must ensure they can withstand the harsh conditions of space. Structural integrity is a primary concern. Space habitats must endure micrometeoroids, radiation, and extreme temperature fluctuations. Pressurization is essential for maintaining a livable environment. Habitats need to be airtight to provide a stable atmosphere for breathing and other life support systems. Thermal control systems regulate the temperature inside the habitat. They prevent overheating or freezing, ensuring a comfortable and safe environment for the crew. Radiation shielding is critical to protect astronauts from harmful cosmic rays. Effective shielding materials and designs minimize exposure and health risks. The habitat must have reliable life support systems. These systems manage air, water, and food supply, recycling resources to support long-term missions. Microgravity affects the stability and functionality of habitats. Design considerations must address how equipment and supplies are secured in a weightless environment. Habitats need efficient waste management systems. Proper disposal and recycling of waste materials are vital for maintaining hygiene and environmental stability. Energy supply and management are crucial for habitat stability. Solar panels and other energy sources must provide consistent and reliable power. Redundancy in critical systems ensures that backups are available in case of failures. This redundancy is vital for maintaining habitat stability and crew safety. Communication systems must be robust and reliable. Continuous contact with mission control is essential for coordinating operations and addressing any issues. Habitats should have medical facilities equipped to handle emergencies. Medical supplies and equipment must be readily accessible and functional. The layout of the habitat impacts daily living and work efficiency. Thoughtful design improves crew comfort, productivity, and mental well-being. Regular maintenance and repairs are necessary to ensure habitat stability. Crew members must be trained to perform routine checks and address any technical problems. The long-term stability of space habitats is fundamental for future missions. Well-designed and maintained habitats enable astronauts to live and work safely in space, advancing human exploration. Centrifugal force is a key concept in creating artificial gravity. It is the apparent force that acts outward on a mass when it is rotated around a center. By spinning a spacecraft or space station, we can simulate gravity using centrifugal force. This force pushes objects and people towards the outer edge, mimicking the effects of gravity. The speed of rotation and the radius of the habitat determine the strength of the artificial gravity. Faster rotation or a larger radius increases the centrifugal force. Designing rotating habitats requires careful engineering. The structure must be able to withstand the stresses of rotation and provide a stable environment. Centrifugal force can create a comfortable living space for astronauts. It allows them to move, exercise, and live more normally compared to a microgravity environment. However, too much rotation can cause discomfort and health issues. The Coriolis effect, caused by the rotation, can lead to dizziness and balance problems. Finding the right balance between rotation speed and radius is crucial. It ensures that artificial gravity is effective without causing negative side effects. Rotating habitats must also manage transitions between rotating and non-rotating sections. Smooth transitions are necessary to prevent disorientation and motion sickness. Centrifugal force impacts the design of interior spaces. Floors, walls, and ceilings must be oriented to match the direction of the artificial gravity. Exercise in a rotating habitat can help maintain muscle and bone health. The simulated gravity provides resistance needed for effective workouts. Centrifugal force also affects fluid behavior. Engineers must account for how liquids move and are stored in a rotating environment. The concept of using centrifugal force for artificial gravity has been explored in various space mission proposals. It remains a promising solution for long-term space travel. Testing centrifugal force in space can provide valuable data. Experiments on the International Space Station and other platforms help refine our understanding. Future space habitats may incorporate rotating sections to provide artificial gravity. This could make extended missions more feasible and comfortable for astronauts. Understanding centrifugal force is essential for advancing space exploration. It offers a practical way to create a livable environment for humans in space. Linear acceleration is another method for creating artificial gravity. This involves continuous thrust in one direction to simulate the effects of gravity. When a spacecraft accelerates linearly, the force pushes objects and people toward the back of the vehicle. This force can mimic the sensation of gravity. The required acceleration to simulate Earth-like gravity is approximately 9.8 meters per second squared. This level of thrust would provide a familiar gravitational pull. Creating sustained linear acceleration poses significant engineering challenges. Continuous propulsion requires substantial energy and efficient propulsion systems. Current propulsion technologies are not yet capable of providing continuous thrust for extended periods. Advanced propulsion systems like ion drives or nuclear propulsion are being explored. Linear acceleration could be used for shorter periods during specific mission phases. For instance, during travel between planets, short bursts of acceleration could provide temporary artificial gravity. The direction of acceleration affects the orientation of the habitat. Spaces must be designed to accommodate changes in force direction and maintain functionality. Linear acceleration impacts the distribution of fluids and other materials. Engineers must consider these effects in the magnetic fields. Offer another intriguing method for creating artificial gravity. By using powerful magnets, it's possible to generate forces that mimic gravity. These magnetic forces can attract or repel objects, creating a pull similar to gravitational attraction. This method relies on the properties of diamagnetic materials, which are repelled by magnetic fields. In space habitats, strong magnetic fields could be used to hold objects and people down. This would provide stability and help simulate a gravitational environment. The challenge with magnetic fields is generating sufficient strength. Superconducting magnets, which can produce very strong fields, are a potential solution. Superconductors work at extremely low temperatures, requiring advanced cooling systems. These systems must be efficient and reliable for long-term space missions. Magnetic fields can also be used in conjunction with other methods. For instance, they could enhance the effects of centrifugal force in rotating habitats. One advantage of magnetic fields is their ability to be turned on and off. This flexibility allows for adjustable levels of artificial gravity depending on the needs of the mission. Research into magnetic fields for artificial gravity is still in the early stages. Experiments are needed to understand the full range of effects on both living organisms and equipment. There are potential health effects to consider. Prolonged exposure to strong magnetic fields might impact human biology, so safety measures are crucial. Magnetic fields can also interfere with electronic equipment. Ensuring the compatibility of these fields with spacecraft systems is a major engineering task. Using magnetic fields to create artificial gravity could also aid in stabilizing loose objects. This would help maintain order and safety in a microgravity environment. Materials science is key to advancing this technology. Developing new materials that respond predictably to magnetic fields can improve the effectiveness of this method. Understanding how magnetic fields interact with the human body is essential. Detailed studies and simulations will help assess the viability of this approach. Combining magnetic fields with other technologies might offer the best solution. Hybrid systems can leverage the strengths of multiple methods to create stable and effective artificial gravity. The potential of magnetic fields for creating artificial gravity is exciting. Continued research and innovation are needed to explore this promising avenue for space travel. Tether systems offer a unique approach to creating artificial gravity in space. By connecting two or more modules with a long cable, we can use rotational motion to generate a centrifugal force. As the tethered system spins, the centrifugal force pulls the modules outward. This creates a sensation of gravity in the direction opposite to the center of rotation. The length of the tether and the rotation rate determine the strength of the artificial gravity. Longer tethers and faster rotation can generate stronger gravitational forces. Tether systems require careful engineering to ensure stability and safety. The materials used for the tethers must be strong enough to withstand the stresses of rotation. Deploying and maintaining tether systems in space presents significant challenges. Precise control of the rotation and tension is necessary to prevent tangling or snapping. One advantage of tether systems is their scalability. They can be adjusted to provide varying levels of artificial gravity based on mission requirements. Tether systems can also be used for propulsion. By ejecting mass along the tether, it's possible to create thrust, assisting in orbital maneuvers. Astronauts living in tether-based habitats would experience a more Earth-like environment. This could help mitigate the health issues associated with long-term exposure to microgravity. Research on tether systems includes studying their dynamics and behavior in space. Experiments on the International Space Station and other platforms are crucial for advancing this technology. Tether systems can also serve multiple purposes. In addition to creating artificial gravity, they can be used for docking, transportation, and even as space elevators. Maintenance and repair of tethers in space require specialized tools and techniques. Ensuring the longevity and reliability of these systems is vital for mission success. The concept of tether systems extends to planetary exploration. Tethers could help facilitate landings and ascents on celestial bodies with varying gravitational fields. Combining tether systems with other artificial gravity methods could enhance their effectiveness. Hybrid approaches can offer more flexibility and redundancy for space habitats. Public and private space organizations are investing in tether research. Collaboration and innovation are driving the development of practical tether-based solutions. Understanding the physics and engineering of tether systems is key to their success. Ongoing research and experimentation will help unlock their full potential for future space missions. Hybrid approaches combine multiple methods to create artificial gravity. These approaches aim to leverage the strengths of each method while mitigating their weaknesses. For example, combining rotational systems with linear acceleration can provide more consistent artificial gravity. Rotational systems generate centrifugal force, while linear acceleration adds a constant gravitational pull. Using magnetic fields alongside centrifugal force is another hybrid approach. Magnetic fields can help stabilize objects and enhance the effectiveness of rotational systems. Hybrid systems offer flexibility in generating artificial gravity. They can adjust the levels of gravity based on mission phases or specific tasks. This flexibility is crucial for long-duration missions. Different activities, such as exercise or medical procedures, may require varying levels of artificial gravity. Combining tether systems with rotational habitats can also be effective. Tethers provide structural support, while rotation generates the necessary centrifugal force. These systems must be carefully designed to avoid interference between different methods. Ensuring compatibility and seamless integration is a significant engineering challenge. Hybrid approaches also allow for redundancy. If one system fails, the other can compensate, ensuring continuous artificial gravity. Research on hybrid systems involves extensive testing and simulation. Understanding how different methods interact in space is key to developing effective solutions. Astronauts living in hybrid habitats would benefit from more stable and adaptable environments. This could improve their overall health and mission performance. Hybrid systems could also be more energy efficient. By optimizing the use of different methods, we can reduce the overall energy consumption of artificial gravity systems. The development of hybrid approaches involves collaboration across various fields. Engineers, scientists, and medical experts work together to create integrated solutions. These approaches are particularly useful for future space colonies. Hybrid systems can provide stable living conditions on the Moon, Mars, or other celestial bodies. Public and private space organizations are actively exploring hybrid methods. This research is essential for advancing human space exploration and long-term habitation. Understanding and implementing hybrid approaches to artificial gravity will be crucial. These innovative solutions will support the next generation of space missions and human settlement in space. The concept of rotational systems is fundamental to creating artificial gravity. By spinning a spacecraft or habitat, centrifugal force can simulate the effects of gravity. As the structure rotates, the force pushes objects and people outward towards the hull. This creates a sensation similar to the gravitational pull experienced on Earth. The speed of rotation and the radius of the habitat are critical factors. Faster rotation and a larger radius generate stronger centrifugal forces. Designing rotational systems involves balancing these factors to avoid discomfort. Too fast a spin can cause dizziness and nausea due to the Coriolis effect. The Coriolis effect occurs when moving within the rotating frame. It can cause disorientation and balance issues if not properly managed. Engineers must consider the size and layout of the habitat. Larger structures with slower rotation rates are generally more comfortable for occupants. Creating a livable environment in a rotating habitat requires thoughtful design. Floors, walls, and ceilings must be oriented to match the direction of artificial gravity. Rotational systems also need reliable power and control mechanisms. Maintaining a steady rotation rate is essential for consistent artificial gravity. Incorporating rotational systems into spacecraft design presents engineering challenges. These include ensuring structural integrity and managing the stresses of rotation. Living in a rotating habitat can help mitigate the health effects of microgravity. It allows astronauts to exercise and perform daily activities in a more familiar environment. Experiments on rotational systems have been conducted in space and on Earth. These studies help refine our understanding and improve the design of such habitats. Future space missions may feature rotating sections or entire habitats. This approach can enhance the well-being and performance of astronauts on long-duration missions. Rotational systems can also be combined with other methods for hybrid solutions. This can provide more flexible and adaptable artificial gravity environments. Public and private space agencies are investing in research on rotational systems. This work is critical for advancing human space exploration and establishing sustainable habitats. Understanding the concept of rotational systems is key to creating effective artificial gravity. It offers a practical solution for long-term human presence in space. Rotating space stations are a practical application of the rotational system concept. These stations create artificial gravity by spinning around a central axis. The centrifugal force generated by the rotation pushes objects and people outward. This mimics the feeling of gravity experienced on Earth. Designing a rotating space station involves careful consideration of the rotation speed and radius. These factors must be balanced to provide effective artificial gravity without causing discomfort. One of the most well-known concepts is the Stanford torus. This design features a large, ring-shaped habitat that rotates to create gravity on its outer edge. The size of the space station affects the rotation rate needed for comfortable artificial gravity. Larger stations can rotate more slowly while still providing sufficient centrifugal force. Structural integrity is a major concern for rotating space stations. The station must withstand the stresses of rotation while maintaining a stable environment for its inhabitants. Interior design is crucial in a rotating space station. Floors, walls, and ceilings need to be oriented correctly to align with the artificial gravity. Living quarters, laboratories, and recreational areas must be designed to function in a rotating environment. This ensures that astronauts can live and work comfortably. The transition between rotating and non-rotating sections of the station requires careful planning. Smooth transitions are necessary to prevent disorientation and maintain safety. Energy efficiency is another important aspect of rotating space stations. The systems used to maintain rotation and artificial gravity must be sustainable for long-duration missions. Rotating space stations offer several benefits for long-term space habitation. They help mitigate the adverse health effects of microgravity, such as muscle atrophy and bone loss. Research on rotating space stations includes both theoretical studies and practical experiments. These efforts aim to refine designs and improve the feasibility of such habitats. International collaboration is key to the development of rotating space stations. Multiple space agencies and private companies are working together to advance this technology. The successful implementation of rotating space stations could pave the way for future space colonies. These habitats would enable humans to live and work in space for extended periods. Understanding the complexities of rotating space stations is essential for the future of space exploration. They represent a promising solution for creating sustainable artificial gravity in space. Angular velocity and radius are critical factors in the design of rotating space stations. They determine the strength of the artificial gravity created by the station's rotation. Angular velocity refers to the speed at which the station rotates. Higher angular velocity increases the centrifugal force experienced by objects inside. The radius is the distance from the center of rotation to the outer edge of the station. A larger radius allows for stronger artificial gravity with a slower rotation speed. Finding the optimal balance between angular velocity and radius is essential. Too high an angular velocity can cause disorientation and motion sickness for the crew. A larger radius generally means a more comfortable living environment. It allows the station to rotate more slowly, while still providing effective artificial gravity. Calculating the necessary angular velocity involves precise mathematical formulas. Engineers must consider the desired level of artificial gravity and the station's radius. The Coriolis effect is influenced by angular velocity. Faster rotations can cause stronger Coriolis forces, leading to potential disorientation. Minimizing the Coriolis effect is crucial for the comfort of astronauts. Proper design and slower rotation speeds can help reduce these effects. Structural engineering plays a key role in managing angular velocity and radius. The station must be strong enough to handle the forces generated by rotation. Material selection is important for the durability and safety of the station. Advanced materials can provide the necessary strength without adding excessive weight. Testing different angular velocities in simulations helps refine the design. These tests ensure that the station can provide stable and comfortable artificial gravity. Adjustable angular velocity systems offer flexibility. Being able to change the rotation speed can help adapt to different mission needs and crew preferences. Crew training is essential for adapting to living in a rotating environment. Understanding the effects of angular velocity and radius helps astronauts acclimate more quickly. Future rotating space stations will likely incorporate modular designs. These designs allow for adjustments in radius and angular velocity as needed. Advancing our understanding of angular velocity and radius is key to developing effective artificial gravity systems. This knowledge will support the creation of sustainable habitats for long-term space missions. The Coriolis effect is a significant factor in rotating space habitats. It arises from the rotation of the habitat and affects the motion of objects and people inside. When you move within a rotating frame, the Coriolis effect causes a perceived deflection. This can make simple movements feel strange and disorienting. For example, if you walk in the direction of the rotation, you feel a force pushing you sideways. This deflection can be confusing and can affect balance and coordination. The strength of the Coriolis effect depends on the angular velocity and the speed of movement. Faster rotation rates and quicker movements increase the effect. Astronauts may experience dizziness and nausea due to the Coriolis effect. These symptoms can impact their ability to perform tasks effectively. To minimize the Coriolis effect, space habitats are often designed with slower rotation speeds. This reduces the perceived deflection and makes the environment more comfortable. Training is crucial for helping astronauts adapt to the Coriolis effect. Simulations and practice in rotating environments can prepare them for these sensations. Designing living and working spaces to account for the Coriolis effect can help. Orientation and layout of the habitat can reduce the need for movements that exacerbate the effect. Understanding the Coriolis effect is also important for planning daily activities. Simple tasks like walking or pouring liquids can be affected by the rotation. Exercise routines must be designed with the Coriolis effect in mind. Specialized equipment and techniques can help mitigate the impact on physical training. Researchers study the Coriolis effect to improve habitat design. Experiments in rotating environments provide valuable data on how to reduce its negative impacts. The Coriolis effect also influences fluid behavior. Liquids in rotating habitats can move in unexpected ways, requiring careful management. Engineering solutions can help counteract the Coriolis effect. Gyroscopes and other stabilizing technologies can be used to minimize rotational impacts. Future space missions will continue to refine methods for dealing with the Coriolis effect. This ongoing research is vital for creating comfortable and functional rotating habitats. Understanding and addressing the Coriolis effect is essential for the success of rotating space stations. It ensures that astronauts can live and work effectively in these environments. Engineering challenges in creating artificial gravity are numerous and complex. One major challenge is designing structures that can withstand the forces generated by rotation. Materials must be strong yet lightweight. Advanced composites and alloys are often used to meet these requirements. The stability of the rotating structure is crucial. Engineers must ensure that the rotation remains constant and that the habitat does not wobble. Energy efficiency is another challenge. Maintaining continuous rotation or acceleration requires a reliable and sustainable energy source. Thermal management is critical in space habitats. Engineers must design systems to manage heat generated by electronic devices and life support systems. Radiation protection is a significant concern. Habitats need effective shielding to protect astronauts from cosmic rays and solar radiation. Life support systems must be highly reliable. These systems manage air, water, and waste, recycling resources to sustain the crew. Creating a habitable environment includes managing air pressure and composition. Oxygen levels, carbon dioxide removal, and humidity control are all vital. Microgravity affects fluid behavior and must be carefully managed. Engineers need to design systems that can handle fluid dynamics in a rotating habitat. Communication systems must remain functional in the rotating environment. Reliable contact with mission control and other spacecraft is essential. Docking mechanisms for rotating habitats present unique challenges. Engineers must design systems that allow for safe and efficient transfer of crew and supplies. Maintenance and repair of the habitat in space require special considerations. Astronauts need tools and procedures to address potential issues without external support. The psychological effects of living in a confined, rotating space must also be addressed. Designing comfortable and mentally stimulating environments is essential for long-term missions. Redundancy in critical systems ensures that a failure does not endanger the crew. Engineers design multiple layers of backup for vital functions. Continuous research and innovation are needed to overcome these engineering challenges. Advancements in materials science, robotics, and space technology will pave the way for sustainable artificial gravity habitats. Constant acceleration spacecraft provide another method for simulating gravity. By accelerating at a constant rate, these spacecraft can create a continuous force that mimics gravity. This acceleration would push objects and people toward the back of the spacecraft, providing a sensation similar to standing on Earth. Achieving Earth-like gravity requires an acceleration of 9.8 meters per second squared. The concept of constant acceleration spacecraft presents significant engineering challenges. Sustaining continuous acceleration over long durations demands advanced propulsion technologies. Current propulsion systems, like chemical rockets, are not suitable for constant acceleration. More efficient propulsion methods, such as ion drives or nuclear propulsion, are being explored. Energy requirements for constant acceleration are immense. Engineers must develop power sources that can sustain prolonged thrust without excessive fuel consumption. Thermal management becomes critical in this scenario. The spacecraft must dissipate the heat generated by prolonged engine operation. Structural integrity must be ensured to withstand the stresses of constant acceleration. The design must prevent deformation or damage under continuous force. Life support systems need to be robust and reliable. These systems must operate efficiently under constant acceleration conditions, managing air, water, and waste effectively. Communication systems must function seamlessly during acceleration. Maintaining contact with mission control is crucial for mission success and safety. The spacecraft's layout must consider the direction of the constant force. Living and working spaces should be oriented to maximize comfort and usability. Crew training is essential for adapting to the constant acceleration environment. Astronauts need to be prepared for the physical and psychological effects of continuous force. Navigational systems must be highly accurate. Precise control over the spacecraft's trajectory is necessary to ensure it reaches its intended destination. Maintenance during constant acceleration presents unique challenges. Astronauts need specialized tools and procedures to perform repairs in this dynamic environment. Research and testing are crucial for developing constant acceleration spacecraft. Simulations and experimental missions help refine designs and address technical hurdles. The potential benefits of constant acceleration spacecraft are significant. They could enable faster travel to distant destinations and provide a more Earth-like environment for long-duration missions. Advancing this technology requires collaboration between engineers, scientists, and space agencies. Together, they can overcome the challenges and unlock the potential of constant acceleration spacecraft for future space exploration. Pulsed acceleration is another approach to creating artificial gravity in space. Instead of continuous thrust, this method uses short, frequent bursts of acceleration. These pulses generate a force that mimics gravity for brief periods. Over time, this can create a cumulative effect similar to constant acceleration. One advantage of pulsed acceleration is reduced energy consumption. It requires less fuel compared to maintaining continuous thrust. Engineers must design propulsion systems capable of delivering precise, controlled pulses. This requires advanced technology and careful calibration. Pulsed acceleration impacts the spacecraft's structure differently than constant acceleration. The design must accommodate the intermittent forces to prevent damage. Life support systems need to adapt to the changing forces. They must function efficiently during both acceleration pulses and the intervals between them. Crew members must be trained to live and work in a pulsed acceleration environment. They need to adjust to the periodic changes in force. This method can reduce the wear and tear on propulsion systems. By operating intermittently, engines can have longer lifespans and lower maintenance requirements. Navigational systems must be highly responsive. They need to adjust the spacecraft's trajectory accurately with each pulse of acceleration. Pulsed acceleration affects fluid behavior within the spacecraft. Engineers must design systems to manage these dynamics and ensure stability. The psychological impact on astronauts is another consideration. The periodic shifts in force can be disorienting and require adaptation. Communication systems must remain functional during acceleration pulses. Reliable contact with mission control is essential for coordinating operations. Research into pulsed acceleration involves extensive testing and simulations. Understanding the effects on both the spacecraft and the crew is critical. This approach could be combined with other methods for hybrid solutions. Integrating pulsed acceleration with rotational systems might enhance artificial gravity. The development of pulsed acceleration technology requires innovation and collaboration. Engineers, scientists, and space agencies work together to refine this promising method. Exploring pulsed acceleration advances our ability to create sustainable artificial gravity. It opens new possibilities for long-duration space missions and deep space exploration. Propulsion systems are the heart of spacecraft mobility. They determine how efficiently we can travel and maneuver in space. Chemical rockets are the most common propulsion system. They provide high thrust but consume a lot of fuel quickly. Ion drives offer a more efficient alternative. They produce lower thrust but can operate continuously for long periods, making them ideal for deep space missions. Nuclear propulsion is another promising technology. It has the potential to provide sustained thrust with high efficiency, essential for long-term missions. Electric propulsion systems use electromagnetic fields to accelerate ions. This method offers a balance between efficiency and thrust. Developing advanced propulsion systems requires significant research. Engineers must find ways to optimize performance while minimizing fuel consumption and weight. Propulsion systems must be reliable and safe. They need to function under the harsh conditions of space without failure. Thermal management is crucial for propulsion systems. Excess heat must be dissipated to prevent damage to the spacecraft. Power supply is another critical aspect. Advanced propulsion systems often require substantial electrical power, necessitating robust power generation and storage solutions. Hybrid propulsion systems combine different technologies. This approach can offer flexibility and efficiency, adapting to various mission phases. Propulsion systems also impact the design of spacecraft. They influence everything from the spacecraft's shape to its internal layout. The choice of propulsion affects mission planning. It determines travel time, trajectory, and the feasibility of different destinations. Maintaining propulsion systems in space presents unique challenges. Engineers must design for easy maintenance and potential in-flight repairs. Future propulsion technologies aim to reduce travel time significantly. Faster propulsion systems could make distant destinations more accessible. Advancements in propulsion systems are key to the future of space exploration. They enable longer missions, deeper exploration, and the potential for human settlement beyond Earth. Energy requirements for artificial gravity systems are substantial. Maintaining continuous rotation or acceleration demands a reliable and consistent power source. Chemical propulsion systems consume large amounts of fuel quickly. This limits their practicality for long-term missions that require sustained artificial gravity. Ion drives and electric propulsion systems are more efficient. They use less fuel but require significant electrical power to operate continuously. Nuclear propulsion offers a potential solution for long-term energy needs. It can provide a steady supply of power and thrust, essential for extended missions. Solar panels are commonly used to generate electricity in space. However, their efficiency depends on the spacecraft's distance from the Sun. Energy storage systems, like batteries, are crucial. They ensure a continuous power supply even when solar energy is not available. Advanced propulsion systems must balance energy efficiency with performance. Engineers work to optimize these systems to reduce overall energy consumption. Thermal management is also a key consideration. Excess heat generated by propulsion and energy systems must be dissipated to maintain operational stability. Energy needs vary depending on the phase of the mission. Launch, transit, and landing each have different power requirements that must be planned for. Innovations in energy storage and generation are critical. Research into new materials and technologies can improve the efficiency and capacity of these systems. Hybrid energy systems might combine solar, nuclear, and other sources. This approach can provide a more reliable and flexible energy supply for spacecraft. Energy management systems must be highly reliable. They need to distribute power efficiently to all onboard systems, including life support and propulsion. The development of sustainable energy solutions is vital for long-term space missions. Ensuring a steady supply of power is essential for the success of these missions. Collaboration between scientists and engineers drives innovation in this field. Together, they work to overcome the challenges of energy requirements for space travel. Advancements in energy technology will support future exploration. Efficient, reliable power systems are key to enabling extended missions and human habitation in space. Feasibility studies are essential for evaluating artificial gravity systems. They assess the practicality and potential challenges of implementing these systems in space missions. Researchers conduct simulations and experiments to test different artificial gravity methods. These studies provide valuable data on how systems perform under various conditions. Simulations help predict how rotating habitats, or constant acceleration, will affect spacecraft dynamics. They also assess the impact on crew health and daily activities. Ground-based experiments mimic space conditions to study artificial gravity effects. These include centrifuge facilities and parabolic flight tests. Feasibility studies also involve analyzing energy requirements. Researchers calculate the power needed to sustain artificial gravity and identify potential sources. Engineering challenges are a key focus of these studies. They examine the materials and designs needed to build reliable and durable artificial gravity systems. Studies also evaluate the cost of implementing artificial gravity. They consider the financial investment required and potential benefits for long-term missions. Feasibility studies must address safety concerns. They assess the risks associated with different methods and develop strategies to mitigate these risks. Human factors are a crucial aspect of feasibility studies. Researchers examine how artificial gravity affects physical and psychological well-being. These studies involve collaboration between various disciplines. Engineers, scientists, medical professionals, and mission planners work together to explore solutions. Feasibility studies inform the design of future space missions. The data collected helps refine artificial gravity concepts and improve their viability. International cooperation enhances the scope of feasibility studies. Shared knowledge and resources accelerate progress and innovation. Long-term studies are essential for understanding the cumulative effects of artificial gravity. They provide insights into how extended exposure impacts crew health and mission success. Pilot missions and prototypes test artificial gravity in real space conditions. These initial trials help identify unforeseen issues and refine system designs. Feasibility studies pave the way for future space exploration. They ensure that artificial gravity systems are practical, safe, and effective for long-duration missions. Magnetic levitation offers a novel approach to creating artificial gravity. By using magnetic fields, objects and people can be suspended, mimicking the effects of gravity. Superconducting magnets are essential for magnetic levitation. They produce strong magnetic fields needed to levitate objects in space. These magnets must operate at extremely low temperatures. Advanced cooling systems are required to maintain their superconducting state. Magnetic levitation reduces the need for mechanical parts. This can lower maintenance requirements and increase the longevity of the system. Controlling the magnetic fields precisely is crucial. Engineers must ensure stable levitation to avoid disorientation or discomfort. One challenge is the impact of magnetic fields on electronic equipment. Shielding and careful design can mitigate potential interference. Magnetic levitation can be combined with other artificial gravity methods. For example, it can enhance the effects of rotational or linear acceleration systems. The health effects of prolonged exposure to strong magnetic fields are not fully understood. Ongoing research is needed to assess any potential risks. Magnetic levitation systems could also be used for transportation within space habitats. Moving objects and people without physical contact reduces wear and tear. Energy efficiency is a key consideration for magnetic levitation. Superconducting magnets require continuous power, so efficient energy management is essential. Research into magnetic levitation involves both theoretical studies and practical experiments. Testing in simulated space environments helps refine the technology. Magnetic levitation offers the potential for creating highly adaptable environments. Adjustable magnetic fields can provide variable levels of artificial gravity. These systems could also be used for scientific experiments. Studying the effects of different gravitational forces on biological and physical processes can provide valuable insights. International collaboration accelerates progress in magnetic levitation research. Sharing expertise and resources helps overcome technical challenges. Advancing magnetic levitation technology is crucial for the future of space exploration. It represents a promising solution for creating sustainable and adaptable artificial gravity in space. Superconductors in space hold great potential for various applications, including magnetic levitation. These materials conduct electricity without resistance at very low temperatures. Using superconductors in space requires advanced cooling systems. Maintaining the necessary low temperatures is essential for their operation. One advantage of superconductors is their efficiency. They can carry large currents without energy loss, making them ideal for power-hungry space applications. Superconductors can generate powerful magnetic fields. These fields are critical for magnetic levitation and other technologies that require strong, stable magnetism. Space presents unique challenges for using superconductors. Engineers must design systems that can operate reliably in the vacuum and extreme temperatures of space. Magnetic shielding is necessary to protect sensitive equipment. Superconductors can produce intense magnetic fields that might interfere with electronics. Research on superconductors includes studying their behavior in microgravity. Understanding how these materials function in space conditions is crucial for their application. Superconducting materials are also used in advanced propulsion systems. They can improve the efficiency and performance of ion drives and other propulsion technologies. Energy storage is another area where superconductors can excel. Superconducting magnetic energy storage systems offer high capacity and rapid discharge rates. Developing superconductors for space involves collaboration across multiple disciplines. Materials. Scientists, engineers, and physicists work together to advance this technology. Superconductors could revolutionize power distribution in space habitats. They enable more efficient energy transfer and reduce the need for heavy, bulky cables. The cost of superconducting materials is currently high. Research aims to find more affordable ways to produce and utilize these materials in space missions. International partnerships enhance the development of superconducting technologies. Shared research and resources help accelerate progress and innovation. Testing superconductors in space is vital. Experiments on the International Space Station and other platforms provide valuable data for refining these systems. The future of superconductors in space is promising. They offer the potential to significantly improve the efficiency and capabilities of various space technologies. Current research in artificial gravity is diverse and rapidly evolving. Scientists and engineers are exploring multiple methods to create a stable and effective artificial gravity environment. On the International Space Station, experiments are conducted to understand the effects of microgravity on the human body. These studies provide valuable data for developing countermeasures. Rotating habitats are a major focus. Researchers are testing small-scale models and simulations to determine the optimal design and rotation rates. Another area of research is linear acceleration. Scientists are developing propulsion systems that can provide continuous or pulse thrust to simulate gravity. Magnetic levitation is being explored through various experiments. These studies aim to understand how strong magnetic fields can be used to simulate gravity and support space habitats. Superconductors are also a subject of intense research. Their potential to generate powerful magnetic fields with high efficiency makes them ideal for space applications. Feasibility studies assess the practicality of different artificial gravity methods. These studies consider factors such as energy requirements, structural integrity, and crew health. International collaboration is key to advancing artificial gravity research. Space agencies, universities, and private companies work together to share knowledge and resources. Research on the psychological effects of artificial gravity is also important. Understanding how different gravity environments impact mental health helps in designing better habitats. Pilot projects and prototype missions test artificial gravity concepts in real space conditions. These missions help identify and address potential challenges. Simulation and modeling play a crucial role in current research. Advanced software tools allow scientists to predict the behavior of artificial gravity systems before physical testing. Experiments with hybrid approaches combine multiple methods to enhance artificial gravity. These studies explore how different techniques can work together to create a more stable environment. The development of new materials is another focus. Researchers are looking for lightweight, strong materials that can withstand the stresses of space and rotation. Long-term studies are essential to understand the cumulative effects of artificial gravity. These studies monitor how prolonged exposure impacts human health and system performance. Current research is paving the way for future space missions. The knowledge gained will help create sustainable artificial gravity environments for long-duration exploration and habitation. Artificial gravity offers numerous potential benefits for space exploration. One of the most significant is the improvement of astronaut health. By simulating gravity, we can mitigate the effects of muscle atrophy and bone density loss. This is crucial for maintaining the physical health of astronauts on long-duration missions. Artificial gravity can also help maintain cardiovascular health. The constant force can prevent fluid shifts that lead to various health issues in microgravity. Mental health benefits are also significant. A stable environment that mimics Earth's gravity can reduce stress and improve overall well-being. Daily activities become easier and more familiar. Simple tasks like eating, drinking, and exercising can be performed more naturally in artificial gravity. Artificial gravity can enhance scientific research. Experiments can be conducted in conditions that more closely resemble Earth, providing more relevant results. Long-term space missions become more feasible with artificial gravity. Crews can live and work in space for extended periods without severe health repercussions. This technology supports the goal of establishing permanent habitats on other planets. Creating a livable environment with artificial gravity is essential for colonization efforts. Engineering systems can benefit from artificial gravity. Fluid management, for example, becomes simpler when liquids behave predictably under a constant force. Artificial gravity can improve safety. It helps secure objects and equipment, reducing the risk of accidents caused by floating debris. Waste management is more effective in artificial gravity. Proper disposal and recycling systems can function more efficiently with gravity's assistance. Artificial gravity can also enhance the psychological comfort of astronauts. The sense of normalcy it provides can improve morale and productivity. Commercial space travel can benefit from artificial gravity. Passengers would experience a more comfortable and familiar environment during their journey. The development of artificial gravity technologies drives innovation. Advances in materials science, propulsion, and energy systems have broader applications beyond space travel. Artificial gravity represents a significant step forward in human space exploration. It addresses many of the challenges associated with living and working in space, paving the way for future missions and habitation. Artificial gravity presents several limitations and challenges. One of the primary challenges is the engineering complexity involved in creating and maintaining these systems. Rotational systems require precise control to avoid disorientation and discomfort for astronauts. Finding the right balance between rotation speed and radius is crucial. Energy consumption is a significant concern. Continuous rotation or acceleration demands a reliable and substantial energy supply, which can be difficult to sustain. Material strength is another limitation. The structures must withstand the forces generated by artificial gravity without compromising safety. Radiation protection remains a challenge. Artificial gravity systems must still provide adequate shielding from cosmic rays and solar radiation. The Coriolis effect can cause disorientation and motion sickness. Engineers must design systems to minimize this effect to ensure the comfort of the crew. Transitioning between different gravity environments can be disorienting. Moving from microgravity to artificial gravity, or vice versa, requires careful management. Maintenance in space is inherently difficult. Artificial gravity systems add another layer of complexity to the already challenging task of spacecraft upkeep. Costs associated with developing and implementing artificial gravity are high. This technology requires significant investment in research, development, and testing. Human health impacts are not fully understood. Long-term studies are necessary to assess the effects of continuous artificial gravity on the human body. Integration with existing spacecraft systems can be problematic. New designs must be compatible with current life support, navigation, and communication systems. Safety is a paramount concern. Any failure in the artificial gravity system could have serious consequences for the crew's health and mission success. Scalability is an issue for larger habitats. Creating artificial gravity for extensive space colonies involves overcoming numerous technical hurdles. Technological readiness is another barrier. Many of the required technologies are still in experimental stages and not yet ready for operational deployment. International cooperation and standardization are needed. Developing globally accepted standards and practices for artificial gravity systems will facilitate their adoption and integration into future missions. Tether mechanics are critical for creating artificial gravity through rotation. A tether system involves connecting two masses with a long, strong cable. As the tethered system rotates, centrifugal force generates artificial gravity. This force pulls the masses outward, creating a sensation of gravity at the ends of the tether. The length of the tether plays a significant role. Longer tethers allow for a slower rotation rate while still producing sufficient artificial gravity. Tethers must be made from materials with high tensile strength. They need to withstand the forces generated by rotation without breaking. Deploying a tether in space is a complex process. It requires precise control to ensure the tether extends correctly and remains stable. Once deployed, maintaining the rotation of the tether system is crucial. Any disruption in rotation can affect the artificial gravity and stability of the system. Engineers must consider the tension in the tether. Proper tension is necessary to keep the system balanced and functioning correctly. Vibrations and oscillations in the tether can pose challenges. These movements need to be dampened to prevent instability and potential failure. The mass distribution along the tether affects its performance. Uneven mass distribution can cause imbalances and complicate the rotation dynamics. Thermal expansion and contraction of the tether must be managed. Temperature fluctuations in space can affect the tether's length and tension. Docking and undocking procedures require special attention. These operations must be designed to avoid destabilizing the tether system. Redundancy and safety mechanisms are essential. Backup systems can help maintain stability in case of tether damage or other issues. Understanding the dynamics of tether systems involves extensive modeling and simulation. These tools help predict behavior and optimize design. Maintenance of tether systems in space is a challenging task. Astronauts need specialized tools and procedures to repair or adjust tethers. Tether mechanics are a promising approach to creating artificial gravity. With continued research and development, they could play a vital role in future space missions. Tether length is a crucial factor in the effectiveness of artificial gravity systems. A longer tether allows for a slower rotation rate, which can reduce the Coriolis effect and make the environment more comfortable for astronauts. The optimal tether length balances the need for effective artificial gravity with practical considerations of deployment and stability. Longer tethers require more precise control and stronger materials to withstand the forces involved. Tether tension is equally important. Proper tension ensures that the system remains stable and that the artificial gravity is consistent across the length of the two. Adjusting the tension in a tether system can help maintain its stability. Active tension control systems can adapt to changes in the environment and the mass distribution along the tether. Tension must be monitored continuously to detect and address any issues promptly. Sudden changes in tension can indicate potential problems, such as tether damage or shifts in mass. The materials used for tethers must have high tensile strength to handle the forces without stretching or breaking. Advanced composites and alloys are often used for their strength and durability. Temperature changes in space can cause thermal expansion or contraction of the tether material. This can affect both the length and tension of the tether, requiring systems to compensate for these variations. Deploying and maintaining long tethers present significant engineering challenges. Precise control mechanisms are necessary to ensure that the tether extends smoothly and maintains the correct tension. Tether length also impacts the design of the attached habitats or modules. These structures must be designed to distribute forces evenly and remain stable during rotation. Vibrations along the tether can affect its tension and stability. Damping mechanisms are needed to absorb these vibrations and prevent them from disrupting the system. The mass distribution along the tether influences the required tension. Uneven distribution can lead to imbalances, making it more challenging to maintain consistent artificial gravity. Tether length and tension also play a role in docking procedures. Ensuring that docking operations do not destabilize the tether system is critical for safety and functionality. Regular inspections and maintenance are required to ensure the integrity of the tether over time. Astronauts must be trained to handle these tasks effectively in the space environment. Research and testing are ongoing to optimize tether length and tension control. Advances in materials science and engineering techniques continue to improve the viability of tether-based artificial gravity systems. Understanding and managing tether length and tension are essential for the success of tether systems in creating artificial gravity. These factors determine the stability, effectiveness, and safety of the system, making them a focal point of ongoing research and development. Current proposals for artificial gravity systems are diverse and innovative. One popular idea involves rotating space habitats, which create centrifugal force to simulate gravity. NASA and other space agencies are exploring the concept of a rotating space station. Designs like the Stanford Torus and the O'Neill cylinder are being studied for their feasibility and practicality. Another proposal focuses on using linear acceleration. Spacecraft would accelerate continuously to provide a constant force, simulating gravity throughout the journey. Magnetic levitation is also being considered. This method uses strong magnetic fields to create a gravitational pull, potentially useful for small-scale habitats or specific areas within a spacecraft. Tether systems are gaining interest for their simplicity and effectiveness. By connecting two modules with a long tether and spinning them, artificial gravity can be generated at a relatively low cost. Hybrid approaches combine multiple methods to optimize artificial gravity. These systems might use both rotational and linear acceleration techniques to provide a more adaptable environment. The European Space Agency is investing in research on artificial gravity. Their studies aim to develop sustainable solutions for long-duration missions to the Moon and Mars. Private companies like SpaceX and Blue Origin are also involved. These firms are looking at innovative ways to incorporate artificial gravity into their spacecraft designs for commercial space travel. The idea of modular habitats is being explored. These habitats can be adjusted and expanded, allowing for flexible artificial gravity solutions depending on the mission's needs. Research on artificial gravity isn't limited to large space agencies. Universities and research institutions worldwide are contributing valuable insights and technological advancements. International collaboration is crucial. Joint missions and shared research help accelerate the development of viable artificial gravity systems. Pilot projects are being proposed to test these concepts in space. These small-scale experiments will provide data on the practicality and effectiveness of different methods. Some proposals focus on specific use cases, such as artificial gravity in medical modules. These areas would help treat astronauts suffering from the effects of prolonged microgravity. Advanced computer simulations are aiding these proposals. Simulations allow researchers to model and predict the performance of artificial gravity systems before physical prototypes are built. The current proposals represent a blend of creativity and practicality. They aim to solve one of the biggest challenges of long-term space exploration by making life in space more sustainable and comfortable. Artificial gravity has several advantages. It can significantly improve astronaut health by mitigating the effects of prolonged weightlessness, such as muscle atrophy and bone density loss. It also enhances cardiovascular health by promoting proper fluid distribution in the body. This can prevent complications associated with microgravity. Artificial gravity can improve daily living conditions. Tasks like eating, drinking, and using the restroom become more straightforward and less messy. Another advantage is the potential for better sleep patterns. With a more Earth-like environment, astronauts might experience more restful and regular sleep cycles. Scientific experiments could yield more Earth-relevant results. Artificial gravity can help simulate conditions similar to those on our planet, making research findings more applicable. However, there are significant drawbacks to consider. One major challenge is the complexity and cost of creating artificial gravity systems, which require advanced technology and significant investment. Energy consumption is another concern. Maintaining systems like rotating habitats or continuous thrust demands substantial power, complicating mission planning and sustainability. The Coriolis effect in rotating systems can cause disorientation and motion sickness. Engineers must carefully design habitats to minimize these effects. Maintenance in space is inherently difficult. Artificial gravity systems add another layer of complexity, increasing the risk of failure and the need for repairs. Safety is a paramount concern. Any malfunction in the artificial gravity system could pose serious risks to the crew's health and mission success. Transitioning between different gravity environments can be challenging for astronauts. The shifts can be disorienting and require adaptation time. The physical and psychological impacts of artificial gravity over the long term are not fully understood. More research is needed to assess potential health risks. Spacecraft design must accommodate these systems, potentially reducing available space for other essential functions and equipment. Artificial gravity systems might interfere with other spacecraft operations. For instance, strong magnetic fields could affect sensitive instruments and electronic systems. Despite these drawbacks, the potential benefits make artificial gravity a compelling area of research. With continued innovation and collaboration, the challenges can be addressed, paving the way for safer and more comfortable long-duration space missions. Implementing artificial gravity systems presents numerous challenges. One major hurdle is the engineering complexity involved in designing and building these systems. Structural integrity must be ensured to withstand the forces generated by artificial gravity. This requires advanced materials and precise construction techniques. Maintaining continuous rotation or acceleration demands a reliable power source. Energy efficiency and sustainability are critical factors in the design process. Spacecraft need to be carefully balanced to prevent wobbling or destabilization. Any imbalance can affect the effectiveness of the artificial gravity system. Deploying and maintaining tether systems in space is particularly challenging. Tethers must be strong, flexible, and capable of being deployed and adjusted as needed. Thermal management is another concern. Systems must be able to dissipate the heat generated by propulsion and other onboard systems to prevent overheating. Ensuring compatibility with existing spacecraft systems is essential. Artificial gravity systems must integrate seamlessly with life support, navigation, and communication systems. The Coriolis effect in rotating habitats can cause disorientation. Engineers must design environments that minimize this effect to ensure astronaut comfort and safety. The transition between different gravity environments can be disorienting for astronauts. Training and adaptation strategies are necessary to help crews adjust. Maintenance and repair of artificial gravity systems in space require specialized tools and techniques. Astronauts need to be trained to handle these tasks effectively. Cost is a significant barrier to implementation. Developing and deploying artificial gravity systems is expensive, requiring substantial investment and resources. Safety protocols must be rigorously tested and enforced. Any failure in the artificial gravity system could have serious consequences for the crew and mission. Human health impacts need to be thoroughly understood. Long-term studies are necessary to assess the potential physical and psychological effects of artificial gravity. International cooperation and standardization are vital. Developing globally accepted standards and practices can facilitate the adoption of artificial gravity systems. Overcoming these implementation challenges requires ongoing research, innovation, and collaboration. As we continue to advance our understanding and technology, the potential for successful artificial gravity systems becomes more achievable. NASA's artificial gravity research is at the forefront of space exploration innovation. The agency is investigating various methods to create and sustain artificial gravity for long-duration missions. One focus is on rotational habitats. NASA is studying the feasibility of rotating sections within spacecraft to generate centrifugal force. Experiments are conducted on the International Space Station. These studies help understand how artificial gravity affects biological systems and equipment. NASA collaborates with universities and research institutions. This partnership broadens the scope of research and accelerates technological advancements. Simulation and modeling play a crucial role. NASA uses advanced software to predict the behavior of artificial gravity systems before physical testing. Pilot projects test small-scale models in space. These experiments provide valuable data on the practicality and effectiveness of different methods. NASA's research includes studying human factors. Understanding how astronauts adapt to artificial gravity environments is key to designing comfortable and effective systems. The agency is also exploring hybrid approaches. Combining rotational and linear acceleration methods might offer more adaptable solutions. Energy efficiency is a critical aspect of NASA's research. Developing sustainable power systems is essential for maintaining artificial gravity on long-duration missions. Radiation protection is another focus. Ensuring that artificial gravity systems also shield astronauts from cosmic rays is a priority. NASA's research extends to potential missions to Mars. Artificial gravity could play a vital role in maintaining crew health during long journeys to the Red Planet. Collaboration with international space agencies enhances NASA's efforts. Joint missions and shared research help overcome challenges and accelerate progress. The research includes the impact of artificial gravity on fluid behavior. Understanding how liquids move in these environments aids in the design of life support systems. NASA's studies also consider the psychological effects of artificial gravity. Ensuring mental well-being is crucial for the success of long-term space missions. NASA's ongoing research is paving the way for future exploration. The knowledge gained will help create sustainable and effective artificial gravity systems, enabling human presence in space for extended periods. The European Space Agency, or ESA, is also deeply involved in artificial gravity research. Their studies complement NASA's efforts, focusing on the practical implementation of artificial gravity systems. ESA is investigating rotating space habitats. They are testing small-scale models to understand the dynamics and potential challenges of these systems. Collaboration with international partners is a key aspect of ESA's research. Working with other space agencies and institutions helps share knowledge and resources. ESA's experiments on the International Space Station are crucial. These experiments provide real-world data on the effects of artificial gravity on biological systems. Simulation and modeling are integral to ESA's approach. Advanced computer simulations help predict how artificial gravity systems will perform in space. ESA is exploring the use of tether systems. Tethered modules can create artificial gravity through rotation, providing a relatively simple and effective solution. Energy efficiency is a major focus for ESA. Developing power-efficient systems is essential for maintaining artificial gravity on long-duration missions. ESA's research includes studying human factors. Understanding how astronauts adapt to artificial gravity environments is crucial for designing comfortable and effective habitats. Radiation protection is also a priority. Ensuring that artificial gravity systems also shield astronauts from harmful cosmic rays is essential for crew safety. ESA is considering the application of artificial gravity for missions to Mars. Maintaining crew health on long-duration missions to the Red Planet is a key goal. Fluid dynamics in artificial gravity environments are another research area. Understanding how liquids behave under artificial gravity conditions aids in the design of life support systems. Psychological effects of artificial gravity are being studied by ESA. Ensuring the mental well-being of astronauts is crucial for the success of long-term space missions. ESA studies include the development of hybrid approaches. Combining different methods of generating artificial gravity can provide more adaptable solutions. Ongoing experiments and pilot projects are essential to ESA's research. These projects test the feasibility and effectiveness of artificial gravity systems in real space conditions. ESA's efforts in artificial gravity research are paving the way for future space exploration. The insights gained from their studies will help develop sustainable artificial gravity environments, enabling extended human presence in space. Private sector initiatives are playing an increasingly important role in artificial gravity research. Companies like SpaceX and Blue Origin are exploring innovative solutions for long-duration space missions. These companies bring significant resources and fresh perspectives to the field. Their involvement accelerates the development and testing of new technologies. SpaceX is particularly focused on missions to Mars. Artificial gravity could be crucial for maintaining astronaut health during the long journey to the Red Planet. Blue Origin is exploring orbital habitats that might incorporate artificial gravity. Their vision includes long-term human habitation in space, making gravity simulation essential. Private companies are also partnering with space agencies. These collaborations help combine public and private expertise, enhancing research and development efforts. Investment from the private sector drives innovation. Increased funding allows for more extensive testing and faster progress in artificial gravity technologies. Commercial space travel is a key area of interest. Companies are developing spacecraft that can provide a more Earth-like environment for passengers, including artificial gravity. Technological advancements from the private sector often have broader applications. Innovations in propulsion, materials, and energy systems benefit both commercial and scientific missions. Private initiatives are also focused on cost reduction. Making artificial gravity systems more affordable will be crucial for widespread adoption in future missions. Companies are exploring modular designs. These allow for flexible and scalable artificial gravity solutions, adaptable to different mission requirements. Research includes advanced simulation and modeling. Private sector tools and techniques help predict system performance and identify potential issues before deployment. Pilot projects and test missions are being conducted. These real-world trials provide valuable data on the feasibility and effectiveness of artificial gravity systems. Human factors research is a priority. Understanding how artificial gravity affects crew health and performance is essential for successful long-term missions. Private sector involvement encourages international collaboration. Partnerships across countries and companies enhance the exchange of ideas and technology. The contributions of private companies are vital for the future of space exploration. Their innovative approaches and substantial investments are helping to turn the concept of artificial gravity into a reality. Notable experiments have provided valuable insights into artificial gravity. These studies are crucial for understanding its feasibility and effects on human health. One significant experiment involved the centrifuge on the International Space Station. This device created varying levels of artificial gravity for biological studies. Results from these studies showed that even partial gravity can mitigate some negative effects of microgravity. This finding supports the potential benefits of artificial gravity for long-term missions. NASA conducted the Human Research Program's Artificial Gravity Pilot Study. This study investigated the physiological impacts of short-radius centrifugation on astronauts. Participants in the study experienced periodic artificial gravity. The results indicated improvements in cardiovascular function and fluid distribution. ESA's bed rest studies have also contributed valuable data. These experiments simulate the effects of microgravity and test countermeasures, like artificial gravity. Findings from bed rest studies show that intermittent artificial gravity can reduce muscle and bone loss. This research is instrumental in developing effective space mission protocols. Another notable experiment was conducted on Earth using the DLR short-arm human centrifuge. This study examined the effects of daily artificial gravity exposure on human subjects. Results indicated that artificial gravity can help maintain muscle strength and cardiovascular health. These findings are promising for long-duration space missions. The Mars Gravity Biosatellite program aimed to study artificial gravity's effects on living organisms. Although the project was eventually cancelled, it provided important groundwork for future research. Japanese space agency JAXA has also contributed to artificial gravity research. Their studies focus on the biological impacts of varying gravity levels on plants and animals. Results from JAXA's experiments help understand how artificial gravity can support life support systems in space habitats. This knowledge is crucial for sustainable long-term missions. Commercial ventures have conducted their own tests. SpaceX and Blue Origin have both included artificial gravity experiments in their mission plans. These private sector experiments complement governmental research, providing additional data and innovative approaches. Collaboration between these entities accelerates progress. Each experiment adds to our understanding of artificial gravity. The cumulative results guide the development of effective and practical solutions for future space exploration. Ongoing research and future experiments will continue to refine our knowledge. These efforts are essential for making artificial gravity a viable component of long-term human spaceflight. Future research directions in artificial gravity focus on refining and expanding current knowledge. Advanced simulations and modeling will play a crucial role in predicting system performance. Long-duration experiments are essential. Testing artificial gravity over extended periods will provide insights into its long-term effects on human health. Developing more efficient propulsion systems is a priority. These systems need to sustain artificial gravity without excessive energy consumption. Hybrid approaches will be explored further. Combining rotational and linear acceleration methods may offer more adaptable and effective solutions. Materials science research will continue to advance. Finding stronger, lighter materials can improve the design and safety of artificial gravity systems. International collaboration will enhance research efforts. Sharing data and resources globally accelerates the development of viable solutions. Space agencies will partner with private companies. This collaboration fosters innovation and leverages commercial expertise and investment. Pilot projects on the International Space Station will expand. These experiments provide real-world data on artificial gravity's feasibility and impact. Psychological research will be prioritized. Understanding how artificial gravity affects mental health is crucial for long-term missions. Human factor studies will delve deeper into adaptation processes. Preparing astronauts for transitions between different gravity environments is essential. Radiation protection research will integrate with artificial gravity studies. Ensuring comprehensive shielding solutions will protect astronauts from cosmic rays. Fluid dynamics in artificial gravity environments will be examined further. Optimizing life support and waste management systems is vital for sustainable habitats. Nutritional studies will assess dietary needs under artificial gravity. Ensuring proper nutrition supports overall health and mission success. Educational programs will train the next generation of scientists and engineers. Preparing skilled professionals ensures ongoing innovation in artificial gravity technology. Continued investment in research and development is key. Advancing artificial gravity solutions will pave the way for safe and sustainable long-term human presence in space. Structural integrity is a critical aspect of artificial gravity systems. Ensuring the strength and stability of rotating habitats or tether systems is essential for safety. Advanced materials are required to withstand the stresses of rotation. Engineers are exploring composites and alloys that offer both strength and durability. Thermal expansion and contraction must be managed. Temperature fluctuations in space can affect materials, potentially compromising structural integrity. Regular maintenance and inspection are vital. Identifying and addressing any structural issues early helps prevent failures. Redundancy in design enhances safety. Backup systems and fail-safes can mitigate the risks associated with structural weaknesses. Computer simulations play a key role in testing structural integrity. These models help predict how materials and designs will perform under various conditions. Real-world testing complements simulations. Deploying small-scale prototypes in space provides valuable data on structural performance. Load distribution is another important factor. Ensuring even distribution of forces helps maintain stability and prevents deformation. Integration with other spacecraft systems must be seamless. Structural components need to support life support, energy, and communication systems without interference. The dynamic nature of space travel presents unique challenges. Structures must be able to withstand impacts from micrometeoroids and debris. Long-term durability is crucial for extended missions. Materials and designs must retain their integrity over months or even years in space. Stress testing in different environments helps identify potential weaknesses. This rigorous testing process ensures that structures can endure the harsh conditions of space. Collaborative research with international partners enhances structural integrity studies. Sharing expertise and resources leads to more robust solutions. Innovations in manufacturing techniques can improve structural components. Advances such as 3D printing in space offer new possibilities for building strong, lightweight structures. Structural integrity is foundational for the success of artificial gravity systems. Ongoing research and development are essential to ensure the safety and effectiveness of future space missions. Power supply and energy efficiency are crucial for artificial gravity systems. Maintaining rotation or linear acceleration requires a reliable and sustainable energy source. Solar panels are a common power source in space. They convert sunlight into electricity, but are less effective farther from the sun. Nuclear power is another option. Small nuclear reactors can provide continuous power but come with safety and regulatory challenges. Energy storage systems are batteries and other storage solutions ensure a steady power supply even when primary sources are unavailable. Efficient energy management is vital. Systems must minimize waste and optimize power use to sustain artificial gravity over long missions. Advances in battery technology are improving energy storage. Higher capacity and faster recharge rates enhance overall efficiency. Energy-efficient propulsion systems are needed. Ion drives and other advanced technologies use less fuel and generate sustained thrust. Heat generated by power systems must be managed. Effective thermal control prevents overheating and maintains system stability. Redundancy in power systems enhances reliability. Backup generators and alternative power sources can ensure continuous operation. Energy harvesting technologies are being explored. These systems capture and convert waste energy, further improving efficiency. International collaboration can accelerate progress. Sharing innovations in power technology benefits all spacefaring nations. Cost-effective energy solutions are necessary. Reducing the expense of power systems makes long-duration missions more feasible. Environmental impact is a consideration. Sustainable energy practices are crucial for the long-term viability of space exploration. Research into alternative energy sources is ongoing. Breakthroughs in areas like fusion power could revolutionize space travel. Balancing power supply and energy efficiency is key to successful artificial gravity systems. Ongoing advancements in this field will support the future of human space exploration. Material science advances are critical for the development of artificial gravity systems. New materials offer the potential for stronger, lighter, and more durable spacecraft components. Composite materials are at the forefront. These materials combine the best properties of different substances, enhancing strength and reducing weight. Advanced alloys are also being developed. These alloys can withstand extreme temperatures and stresses, making them ideal for space applications. Nanotechnology is playing a significant role. Nanomaterials offer unique properties that can improve the performance and resilience of spacecraft structures. Self-healing materials are another exciting development. These materials can repair themselves when damaged, increasing the longevity and safety of space habitats. 3D printing is revolutionizing manufacturing. In-space 3D printing allows for the creation of complex components on demand, reducing the need for heavy and expensive spare parts. Carbon nanotubes are being explored for their incredible strength and flexibility. They could be used in tethers and other critical components of artificial gravity systems. Graphene is another promising material. Its remarkable conductivity and strength make it suitable for various applications in space technology. Materials that can withstand radiation are essential. Radiation-hardened materials protect both the spacecraft and its occupants from harmful cosmic rays. Thermal protection materials are crucial for managing the heat generated by spacecraft systems. Advances in this area help maintain stable and safe temperatures. Lightweight, high-strength materials reduce launch costs. Every kilogram saved in material weight translates to significant cost savings for space missions. Durability is vital for long-duration missions. Materials that can endure the harsh conditions of space over extended periods are necessary for sustainable exploration. International collaboration in material science accelerates innovation. Shared research and development efforts lead to faster advancements and implementation. Cost-effective manufacturing processes are important. Developing new materials that are not only high-performing but also affordable is key to widespread adoption. Continuous research and development in material science will support the next generation of artificial gravity systems. These advances are essential for the success of future space exploration missions. Safety considerations are paramount in the design and implementation of artificial gravity systems. Ensuring the well-being of astronauts is the top priority. Structural integrity is a critical aspect of safety. All components must be rigorously tested to withstand the stresses of artificial gravity. Redundancy is essential in safety systems. Backup mechanisms ensure that if one system fails, another can take over to maintain safety. Continuous monitoring is required. Sensors and diagnostic tools must constantly check the health of the spacecraft and its systems. Training for astronauts is crucial. Crews must be well prepared to handle emergencies and operate safety systems effectively. Emergency protocols must be clear and well rehearsed. Quick and effective responses to any issues can prevent minor problems from becoming major ones. Fire safety is a major concern in space habitats. Materials must be flame-resistant, and fire suppression systems need to be highly reliable. Life support systems must be robust. These systems manage air, water, and waste, ensuring that the environment remains safe and livable. Radiation shielding is vital. Protecting astronauts from cosmic rays and solar radiation is essential for long-term missions. Thermal control is necessary to maintain safe temperatures. Overheating can damage equipment and endanger the crew. Isolation from micrometeoroids is another consideration. Protective measures must be in place to prevent damage from high-speed space debris. Psychological support is part of safety. Ensuring the mental well-being of astronauts helps them cope with the stresses of space travel. Medical facilities must be equipped for various health issues. Providing the necessary tools and supplies ensures that astronauts can receive proper care if needed. Regular maintenance schedules are critical. Preventive maintenance helps identify and address potential issues before they become serious. International standards and regulations guide safety practices. Adhering to these ensures that all space missions meet the highest safety standards. Cost and budget constraints are significant factors in developing artificial gravity systems. These projects require substantial financial investment, often straining available resources. Budget limitations can impact the scale and scope of research and development. Securing sufficient funding is crucial for advancing technology and conducting necessary experiments. Efficient use of resources is essential. Optimizing designs and materials can help reduce costs while maintaining effectiveness and safety. Collaboration with international partners can alleviate some financial pressures. Sharing costs and resources can make ambitious projects more feasible. Private sector investment plays a crucial role. Companies like SpaceX and Blue Origin bring additional funding and innovation, accelerating progress. Cost-effective manufacturing techniques are important. Advances in 3D printing and automated production can lower the expenses associated with building artificial gravity systems. Scaling projects to match available budgets is often necessary. Initial prototypes and smaller-scale experiments can provide valuable data without excessive costs. Long-term investment is crucial for sustained development. Continued funding ensures that research progresses steadily and reaches its full potential. Government support can significantly impact budget constraints. Policies that prioritize space exploration can lead to increased funding and resources. Budgeting for unexpected expenses is also important. Contingency funds help manage unforeseen challenges and keep projects on track. Public interest and support can influence budget allocations. Highlighting the benefits of artificial gravity for future space exploration can garner broader financial backing. Efficiency in project management can reduce costs. Streamlined processes and effective oversight ensure that funds are used wisely. Grants and funding from scientific organizations can supplement budgets. These funds support specific research initiatives and help drive innovation. Balancing costs with technological advancements is a delicate process. Investing in cutting-edge research while managing expenses is key to sustainable development. Long-term planning is essential to address budget constraints. Strategic allocation of resources and phased project implementation can ensure steady progress toward achieving artificial gravity in space. We've covered a lot of ground in this video on artificial gravity and its feasibility for future space missions. From the fundamental principles of gravity to the latest research and technological advances, we've explored the myriad ways in which we might create livable environments for astronauts on long-duration missions. We began by discussing the importance of artificial gravity and why it's crucial for maintaining the health and well-being of astronauts. We then delved into the basic principles of Newton's law of gravitation and Einstein's theory of general relativity, setting the foundation for understanding how gravity works in space. Next, we examined the effects of microgravity on the human body, highlighting the health issues that arise from prolonged exposure to weightlessness. Muscle atrophy, bone density loss, and cardiovascular changes are just a few of the challenges that artificial gravity aims to address. We explored various methods for creating artificial gravity, including rotational systems, linear acceleration, and magnetic levitation. Each method comes with its own set of advantages and challenges, from engineering complexities to energy requirements. Current research and notable experiments from NASA, the European Space Agency, and private sector initiatives provide valuable insights and drive innovation. These studies are crucial for developing practical and effective artificial gravity systems for future missions. International collaboration and ethical considerations play a significant role in advancing space exploration. Working together ensures that space missions benefit all of humanity and adhere to shared ethical standards. We also discussed the societal benefits of space exploration, from technological advancements and medical innovations to environmental monitoring and educational initiatives. The impact of space research extends far beyond the boundaries of our planet. Looking ahead, the long-term vision for humanity in space includes establishing permanent settlements on the Moon and Mars, developing sustainable habitats, and ensuring the well-being of space settlers. This ambitious vision drives ongoing research and development in artificial gravity and other critical technologies. In conclusion, artificial gravity is a key component of our future in space. The continued efforts of scientists, engineers, and international collaborators are bringing us closer to making long-term human space exploration a reality. If you enjoyed this video, please like and subscribe to our channel. Check out the rest of our videos for more fascinating insights into space exploration and other exciting topics. Thank you for watching.